We shall be seeing a lot of this device. It's an air track on which we can carry out some important experiments. Specially shaped metal gliders are used on the air track. At the moment, the glider doesn't move very easily over the track. But there are regularly spaced small holes in each side of the track, and air can be pumped out through them. The glider is lifted by the air, so that it's now riding on a cushion of air, rather like a hovercraft. Now it does move very easily along the track. There's practically no friction. We'll use this air track to examine Newton's laws of motion. Newton's first law of motion tells us that if no forces act on a moving body, it will continue moving in a straight line at the same speed. If we give the glider a push, it will move along the track with practically no friction, so practically no forces will be acting on it, and it should maintain a practically constant speed. We mark its position on the track every 2 seconds.
Mark. 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 Mark.
You can write down the scale readings if you want to work things out for yourself. The glider started at the 50 centimetre mark. After 2 seconds, it was here. After 4 seconds, after 6 seconds, and after 8 seconds. If we plot distance travelled against time taken, we get these points. They lie on a straight line. The fact that it is a straight line shows that the glider was travelling at a constant speed, as it should do by the first law of motion. Newton's second law of motion, a more complicated experiment. We shall start this glider from rest at this point on the scale, the 150 centimetre mark. There's a light thread attached to it, passing over a pulley at the end of the track, and carrying a 2-gram weight. This exerts a constant force on the glider, causing it to be pulled along the track when we release it. Let's stop it here and take a closer look. There's a detector mounted above the track, which causes a counter to run for as long as the white tape on the glider is under the detector. The white tape is 2 centimetres long, and the counting rate is 200 counts per second. See it counting as soon as the white tape's under the detector. The counter's positioned over this point at 141 centimetres. Using this device, we'll be able to work out the speed of the glider when it's travelled the 9 centimetres from the 150 mark, starting from rest. We'll also need to know the time taken for it to travel that distance. Newton's second law of motion tells us that a force applied to a body causes it to accelerate, and the acceleration's proportional to the force. A constant force, like our 2-gram weight, should cause a constant acceleration. We'll see if it does. It took just under 3 seconds to travel the distance, 2.9 seconds. And it was taking 58 200ths of a second to travel 2 centimetres, the length of the tape, when it passed the detector. Now let's move the detector further along the track. We're now going to measure the speed of the glider when it's travelled further than before from rest at the 150 mark. We'll measure it when it gets here, to the 104 centimetre mark. Once again, the weight will exert a constant force on the glider, causing it to accelerate. It took 6 seconds exactly to reach the 104 mark. and 28 200ths of a second to travel 2 centimeters beneath the detector. We move the detector, the finishing post, again. It's above the 73.4 centimeter mark, 73.4 centimeters. We start from rest at 150 centimeters again. It took just under 8 seconds, 7.9 seconds. And the counter measured 22 200ths of a second while the 2 centimeter tape passed beneath the detector. A final position for the detector at 42.6 centimeters. It took 9.4 seconds to reach the detector, and was then traveling 2 centimeters in 19 200ths of a second. To see whether the experiment confirms the second law of motion, 3 graphs can be plotted. First, if the velocity attained by the glider at time t equals v and the acceleration is a, then v should equal a t, so that a equals v over t. If we plot velocity against time from the experiment, we get these points. The straight line shows that the acceleration was constant, and we can work it out from the slope of the graph, since a equals v over t. We divide this distance into this to get the acceleration. Again, for a body starting from rest, if the distance traveled in time t equals s and the acceleration again equals a, if the acceleration is constant, then s equals a half at squared. So a, the acceleration, equals 2s over t squared. If we plot our measurements of distance s against t squared, we again get a straight line. We can again work out the value for the acceleration if we measure the slope, and it should be the same value as before, within experimental error. Finally, if the velocity at distance s equals v, and a is again the acceleration, then v squared equals 2as. So a equals v squared over 2s. If we plot our experimental results, v squared against s, the distance, again, we get a straight line. From our equation, we can calculate yet another value for a using the slope of the graph. All 3 straight line plots show that our constant force did produce a constant acceleration. This confirms the second law of motion. The second law still holds if we apply a constant force which acts against the motion of a body. We get a constant negative acceleration, a deceleration. The body slows down, then stops. This happens when a car driver brakes hard without skidding. The car decelerates and stops after a certain distance. This police driver will brake from 30 miles per hour as he passes the cross on the road. See how far he's traveled before stopping. That was from 30 miles per hour. Now he's going to come along faster, but starting to brake to apply the constant force at exactly the same spot on the road. 40 miles per hour. This is where he stopped from 30 miles per hour. See how much further he took at 10 miles an hour faster. Now he's going to come along faster still. At 60 miles per hour. He stopped here at 40 miles per hour and here at 60. Now at 70. This takes a lot of skill not to lock the wheels and skid. That extra 10 miles per hour from 60 to 70 meant that he took even further to come to a standstill. It's very important for all drivers to realize how much further they travel before they stop, the faster they're going. Look at the equation, derived from the second law of motion. S, the distance traveled under the influence of the force applied to a moving body, depends upon the acceleration A, in our case a negative acceleration when we apply the brakes, and upon the speed the body's traveling, v. v squared equals 2as. So S is proportional, not to the speed, but to the speed squared. That's why a quite small increase in speed means a big increase in your stopping distance. Afterwards, look up stopping distances at different speeds in something like the Highway Code. Once again, physics in action on a very important subject, road safety. Now for another air track experiment. These two gliders have each the same mass, and there's a magnet at one end of each. These magnets are so mounted that they have like poles facing outwards, so they repel each other. We'll use these gliders to demonstrate Newton's third law of motion. The same kind of detector as before, which will measure the time it takes for this strip of white tape to pass beneath it. The timer records 20ths of a second this time. The two identical gliders, with magnets attached, are tied together with a piece of thread, so that they can't push each other apart. Each has a strip of white tape of the same length, and there are two detectors and counters, as you can see. See what's happened? Each glider has gone off at the same speed. Let's try it again. Two gliders of the same mass, each exerting a force on the other. Again, the same speed, to within the experimental error. Once again. They move off at the same speed, but in opposite directions, so the value for their momentums, the mass times velocity, must be equal but opposite. Suppose we now try this setup. The right-hand glider is really two gliders fixed together, so it has twice the mass of the one on the left. But one half of this double glider is black on top, so it doesn't affect the detector, and there's still the same length of white tape on the other half. If each exerts the same force on the other, they should move apart with equal but opposite momentum. If one's got twice the mass of the other, it should move off at half the speed, and it does. The tape on the right takes twice as long to pass beneath the detector. The third law of motion states that if body A exerts a force on body B, then body B exerts the same force on A, which is exactly what this experiment shows. A certain force produces a certain momentum, and each glider gains equal but opposite momentum to the other. The momentum to begin with is zero. Neither glider is moving. When they push each other apart, each acquires equal but opposite momentum to the other, so the total momentum remains zero. Again, we're witnessing instances of the law of conservation of momentum. Momentum, mass times velocity, can neither be created nor destroyed. Once again, these laws of physics have important effects on our lives. Let's take just one example, but a very important one: safety in motor cars. These parents use safety seats and seat belts whenever they ride in their car. Let's look at a very dramatic demonstration of the importance of seat belts and an application of ideas about momentum. This is a test rig at the British Standards Institute's laboratories at Berkhamsted. A dummy representing a baby is placed in a carry cot, which is properly strapped to a car rear seat. The seat is mounted on a trolley attached to a sort of gigantic catapult. It can be pulled back, then let go. When the trolley reaches 30 miles per hour, it is suddenly stopped dead, as if in a bad car crash.
Stand by. 5, 4, 3, 2, 1.
Watch that again in slow motion. What's happened to the momentum of the trolley, seat, cot and dummy? It can't be destroyed. Where do you think it's gone? Anyway, the baby would probably be safe if a bit shaken up. But suppose the carry cot wasn't secured to the seat. The result would be very different.
2, 1.
In slow motion, you can see how the momentum of the cot plus baby remains the same after the collision. The cot goes sailing on until it hits something like the windscreen or some other lethal object. Here's a dummy representing an older child, properly strapped in using a seatbelt and a child's safety seat.
Stand by. 5, 4, 3, 2, 1.
Once again, what happens to the momentum? It's got to be conserved, remember. It can't just disappear. And now suppose there's no seatbelt. What you're about to see could happen to anyone in a motor car, child or adult, not using a seatbelt. The momentum of the dummy is conserved. The rest stops, but it goes sailing on. This can mean horrible injuries and even death if you don't use your seatbelts. The laws of motion govern many of our activities. We've taken only 2 examples in this film. There are many others, but perhaps those to do with staying alive on the roads are as important as any.